We get our fair share of swinging, okay? One of the things we study in meteorology is that the more in the center of a landmass you are, like us here in the Midwest, the more you're just going to have those crazy swings because you don't have the oceans to kind of moderate your temperatures. Okay, so this would have no seasons. Planets out there whose axis of rotation is not tilted do not have seasons. Okay, all right, so let's tilt it. Remember I told you it got hit? Ah, there we go. So the way this works is this is the sun, this is the earth, and this is always pointed at Polaris. Okay? Now I know it looks like I'm kind of making a circle, but Polaris is so far away that it is always pointed at Polaris, trust me. So here I have to keep my tilt the same. Okay? My tilt is the same. All the while it's spinning like this. Okay, but my tilt is the same. The same. Okay. So does this look like the northern hemisphere is tilted towards the sun? Okay. This actually is one of our solstices. We have two extreme solstices and two kind of wimpy equinoxes. Okay, so we have the summer solstice. Okay. Over here we have our first of two equinoxes. This is the fall or the vernal equinox. Okay. So if it takes 12 months to go around, this would take 3 months, right? Because I'm going to go in quarters. Okay, so 3 months from here to here. Okay, so this is the fall equinox. The thing about the equinoxes is that as the Earth spins, all latitudes get equal daylight and equal nighttime. So 12 hours and 12 hours. And then we go over here, 3 months from the equinox, and this is our other solstice. Does it look like the northern hemisphere is tilted away from the sun? Yeah. Actually, so this is our winter solstice. Okay, then over here we get our spring equinox. Okay, and then over here we're back to summer solstice. So that's kind of how it goes. But one of the things, and it's on a slide coming up, but do you see where, for instance, as we're experiencing summer, notice what they're experiencing, winter. Okay. And
So then when you're in the
this one?
fall and the spring, you're in front and in back, whereas you're in the winter and the summer.
That's right, exactly. Yep, you had the tilt right. That is exactly right. Perfect. That's it.
It took me a bit to understand it when I was reading it, but yeah.
Yeah, very good, Susan. Sounds like you got it. So, did you fill in the blank there? I just now finally put that up there.
Oh, okay. I forget sometimes.
Okay. So it looks like we all kind of buy this whole Earth's tilted axis of rotation, and you can almost kind of see that here in the summertime it's like we're leaning in. But I don't want you to think that because we're leaning in, it's the distance that makes us warmer, because it's not. Okay, this whole tilting in and making us warmer temperatures does, I guess, kind of three things. One is as we spin, our daylight hours are more over here. Number of daylight hours in the summer, a lot in the northern hemisphere, okay? So in fact, I kind of, with regard to daylight hours, made this slide. So over here on the first column, you see the winter solstice, the vernal or the spring equinox, maybe you said vernal wrong, the vernal or spring equinox, the summer solstice, and the autumnal equinox. Okay, and they happen 3 months apart, so December, March, June, and September, around 21st, 22nd-ish. And the winter solstice over here, okay, as the Earth rotates, as the Earth spins through the course of the one day, okay, if you are above a latitude of 66 1/3 degrees, okay, if you're up here, closer to the North Pole, actually you're going to have constant nighttime. There's like a movie out there, is it Daybreak or something, with vampires, and okay, and they actually, this would be a great place to live if you're a vampire, okay, because there's no daylight. Then the equinoxes, we have equal daylight and nighttime. Then over here, the other extreme, actually, and I have a picture to show you this, okay? Whoops. This one right here, this picture is showing you the summer solstice. So as the Earth spins on its axis one day, actually the way it's tilted like this, if you are above the same latitude, 66 1/3 degrees north, okay, the sun will never set. So actually this is like 24 hours worth of sun. You just see it kind of going higher in the sky for noon, a little bit lower, you know, for midnight. Okay. So, extremes, extremes. Okay, so this is kind of a standalone topic. If I were to ask you how many hours in a day, you would say there's 24 hours in a day. Okay, 24 hours to do this one time. But what you're doing actually is saying what a solar day is to complete one spin. Okay? There's something called a sidereal rotation, or a sidereal day. Okay, and the way I remember the word sidereal day is I see the word real in sidereal. I'll show you where sidereal is. I don't know if this is a word you need to fill in or not. Let's find sidereal. Down here, I see the word real in sidereal. Real meaning 360 degrees. So here's how that works. It's kind of strange. What they're trying to show you with that guy is basically he is the Earth, and he is going to complete one spin on his axis. That would be one day, right? But the thing is, and this figure kind of shows you that, he's not only spinning on its axis to try to complete one day, he is also orbiting the sun. Okay? So this would be if the Earth weren't orbiting the sun, the 360 degree day, the sidereal day, and the solar day would be the same. But here's the deal. As he relocates, here, I'm going to spin once, okay, and then I'm going to relocate. Okay, I am not at the same relative position of the sun. I need to go 4 more minutes, okay, to do that. Okay, so this is a sidereal day, okay, but I'm moving, so I need to kind of go 4 more minutes. So the solar day is 24 hours. The sidereal, the sidereal day is 4 minutes less than that. So 23 hours, 56 minutes. All right. So back to the whole angle thing. I already told you that because the Earth's axis of rotation is tilted, that's why we have different numbers of daylight hours, the extremes at the solstices and equal at the equinoxes. The other thing, though, is an angle thing. So the angle kind of in meteorology we talk about this kind of has 2 consequences. Okay? So anytime you have a large angle like this, you get lots of E. E meaning energy from the sun. Okay, so this is a large angle. Large angle. Anytime you have the sun has a small angle, like this, you get not much energy. Okay? And this is what we call, this would be a small angle. So here's one for you. Haven't you noticed, like in the dead of winter, you go out to find the sun and the sun never rises very high? Actually, this right here is showing you, she's looking for the sun, and these are different times of the year, showing kind of the movement of the sun across her local sky. In the wintertime, it rises in the east and sets in the west, but it's really pretty low. Okay? The equinoxes, a little bit higher. Okay? And in the summertime, it's as high as it's going to be. So we have a great angle. That means more energy. And the thing about it is actually when the sun is kind of low on the horizon, like in wintertime, it doesn't rise very high, it really gives you a different light. Because the Earth's atmosphere causes it to, some of the sunlight, I said less energy, and the Earth's atmosphere robs some of those colors of light. What this figure is trying to do actually is kind of emphasize, I don't know if you can see, this amount of the Earth's atmosphere at a low angle, okay, and this amount of the Earth's atmosphere at a high angle or great angle. So the whole Earth's atmosphere depleting the energy is a player. Okay. This one down here is kind of a famous where is the sun throughout the year sort of thing. You see it goes high at the summer solstice, low at the winter solstice, and kind of crosses paths at the equinoxes. All right. So I really, when I show this to you, it almost to me looks like we experience summer because we're a little bit closer. But that's not it. We experience summer because the number of daylight hours are greater, the sun's rays are more direct. Okay, and over here we experience winter because the number of daylight hours is less, and there's more. The angle with the sun is a lot smaller. Okay, so here's the deal. If it were kind of a situation of proximity, the thing is, how do I say this? Okay, this is winter, right? This is winter. Actually, and what is down here, this is summer, right? For the southern hemisphere, winter for the northern hemisphere. Here, we are at what we call perihelion. And perihelion is when you are closest, when the planet is closest to the sun. So we're like 3% closer to the sun there in our winter. Sometimes students will say, well, does that make their summer worse? No, because distance isn't really what it is. Okay, we are perihelion here about January 3rd or so, actually. Okay, and here we're at what we call aphelion, which means we're the furthest from the sun, okay, by 3%, but go figure, it can get pretty darn hot. So it's not proximity, it's not distance, it's those other things I talked about. All right, so the Earth's tilted axis of rotation, it stays about 23.5 degrees, but it will do this kind of coning thing called precession. And so I'm trying to kind of, you see how I'm kind of trying to keep the same angle, but kind of cone it, right? So right now we're pointed to Polaris, right? And like this one shows you, okay, right now we're pointing to Polaris, but actually over the course of, what is it, 26,000 years, okay, we have come full circle. We used to, about 13,000 years, I think it says ago, we used to be pointed to Vega, okay, and so Bubing, I don't know the names of all these stars. And so, but we stay tilted. Here's kind of, and it takes a long time to do that, but a subtle thing that happens when, it's called precession, when precession occurs, a subtle thing that happens is our solstices and equinoxes will vary as that happens, okay? It'll be really subtle, but have you ever heard of precession of equinoxes? Precession of equinoxes, okay. Okay. All right. The Earth's moon, excuse me, and its motion. Okay, so switching gears, put away my Earth's axis of rotation. Now, this is probably going to be the Earth, right? Switching from the sun to the Earth. So that's the Earth, and I am the moon. So you know that the moon, orbits the Earth, and guess what direction? Counterclockwise. Okay, so the moon orbits the Earth, while the Earth orbits the sun. So here's the deal, though. It's got this cool thing called synchronous rotation, and I have a slide just for synchronous rotation. But it takes about 29.5 days to complete one orbit. And it also spins on its axis of rotation 29.5 days. Okay? Called synchronous rotation. So the rotation and the orbit are connected. So just like we kind of had perihelion and aphelion, we also have perigee and apogee. Hope I said that right before. So that's to say that the Earth is not dead center in the orbit. Sometimes the moon is closer, we call that perigee, and sometimes the moon is farther, we call that apogee. And actually, we have something very practical coming up with regard to apogee and perigee. What's that?
These chairs suck.
They do. I've seen like nurses especially bring like little cushions to sit in the chairs, and I know why they do that. Feel free to like stand up, really. Yeah. They are not good. Or take a couple of chairs. I don't know how that would help you. So if you guys have heard that there's a supermoon coming up, it's probably on Facebook and everything. Okay, so all a supermoon means is basically you have a full moon when the moon, it's full phase, and we'll talk about full phase when it's got its shortest distance to the Earth. Okay, that's called perigee. Okay, that makes it a supermoon. And we have back-to-back supermoons, I think, in September and October. So one of the things before I move on, in case I forget, so do you see, so it takes 29 and a half days to go, to make one orbit, the moon. So that's close to 28. 29 and a half is close to 28, I suppose. The cool thing about that is 28 you can divide by 7. The reason I mention this is it takes about 4 weeks. That's what was going to be my point. It takes about 4 weeks. 4 weeks, which is what, 4 times 7 is 28 days. It takes about 4 weeks to complete one time for the moon to go around the Earth once. So that's kind of helpful. All right. So in case you didn't quite get this yet, and I'm sure you already know this, stars make their own energy, right? Nuclear fusion in the cores, controlled nuclear fusion in the cores of stars, right? But planets don't and moons don't. So the only reason we can see them is because light must be hitting them and reflecting off of them. Light from something else. So the light from the sun, shown here. So we have light from the sun. Actually, this little one down here is going to start kind of the idea of how the phases of the moon come about. Okay, so this one down here. Okay, so basically notice that in all cases we have a half of the moon illuminated all the time. Half of the moon is illuminated. The reason we see a different kind of, like a full moon or crescent moon or quarter moon, has to do with kind of how much of that half we get to see. All right, phases of the moon, speaking of. So before we jump into phases, okay, I want to make sure we're on board with what the term Terminator. Has anybody here seen the Terminator? I saw movies this summer. It's pretty good. I liked it. So what a Terminator is like the slide says, basically, like if this is, I'll go ahead and make it, split it like this, and this is light, the sunlit part, okay, and this is dark. Okay, this part right here is the Terminator. Knowing that the term Terminator is almost like a practical thing, in that if somebody wants to kind of enjoy looking at the moon through binoculars or probably more likely a telescope, they're going to kind of run their telescope along the Terminator, because that's where you're going to kind of see the terrain of the moon through the telescope. After break, I'll pull up some of my, I'll try not to, like, somebody shows you home videos, you're like, oh my gosh. But I'll try to pull up some of my videos that I've shot of the moon through my telescope. It's right along the Terminator. Okay, so phases of the moon. Here we go. Not too bad. So let's try to kind of recreate what she did, if that's okay with you. Let's go ahead and I'm going to make this the Earth. I'm going to be the moon. And just like this orientation, I'm going to put the sun over here. The sun is going to be this. Okay, the sun is right here. Right. So if we start with kind of where it's blue, right there, okay? So I am the moon, okay? Notice that, and I'm going to go ahead and do this on purpose. If you're on Earth, you see my front side, but it's my back side that's lit up from the sun, okay? And it's all about counterclockwise. So I told you 28 days, right? 28 days to do one of these. Let's divide that in quarters, okay? So in 1 week, in quarters, I'm going to be right here. Okay, so my back side is lit up, okay? So actually, if you're here, you're going to see basically this side lit up and this side dark. Okay, this side lit up and this side dark. You are going to see you're going to see a quarter moon. Okay, so actually this is what we call first quarter. 1 week later, I'm going to be over here again. Moon, Earth, Sun. Sun is over there. Sun is my full. I'm lit up, totally lit up. And let's just for kicks pretend, and not pretend, but usually the Earth is out of the way. The Earth doesn't block the sun from me. So this is where you see a full circle. This is a full moon. Okay. 1 week later, I'm over here. Okay. So this part is lit up. Excuse me, this part is lit up. So actually, you're going to see this part lit up, this part's dark. Okay. 1 week later, I'm over here again. I'm back to what we call new moon. Back's lit up. Okay, but you can't see the back. Okay, you don't see anything. It's a new moon. Okay, so that's kind of why it works well for kind of the week, each week you get kind of a new major phase. The major phases being full first quarter. Let's go this way, sorry. The major phases being new moon, first quarter, where'd it go? Full, third quarter, last quarter, okay? Those would be like a week apart. Very good. I'm not going to necessarily belabor it, but also I really like on this slide, it tells you about when the moon will rise. Okay? The thing about the moon, and just kind of see if this is right. Basically, the moon kind of follows the sun sometimes, and sometimes it looks like it's leading the sun. So right here at first quarter, think about it this way. In a daytime sky, you know, the sun rises first and then the moon follows. Okay, the sun rises and then the moon follows. Over here in the full phase, check it out. On Earth, basically, as the sun is setting, the moon is rising. They're from horizon to horizon. Okay? Over here, it kind of looks like the moon kind of precedes the sun in rising. Okay? And here, of course, they're right next to each other. They rise about the same time. It's a new phase. All right, so the main phases are new, first quarter, full, third quarter, and they're back to new again. Now, but there are some things in between, and that's what this slide is about. So between first quarter, okay, well, let's just do it this way. When the moon is getting more illuminated, it's not getting more illuminated, but when we're seeing more and more of the illuminated side of the moon, that would be from new to full. It's getting larger. We call that waxing. Okay? And waxing always will go from the right back to the left again. And also waning will go from the right back to the left again. So can you kind of see that? What I mean to say is what's ever on the right is going to proceed to the left, right? Okay, waxing. So now we have a couple more terms, the term crescent and gibbous. Okay, crescent is less than a quarter, gibbous is greater than a quarter. So we have a waxing crescent before first quarter, and we have a waxing gibbous between first quarter and full. Then we have these other deals, where from full, you see, again, from left to right, it becoming, in this case, not more illuminated, but it is becoming less illuminated from right back to left again. Whatever you see on the right, it's kind of contaminating the left. That's the way I think of it. Okay? So in these cases, it's getting smaller and smaller. We call that waning. And again, we have kind of the gibbous and crescent terms apply. If it's larger than a quarter after full, okay, it's a waning gibbous. And if it's smaller than a crescent after third quarter, it's waning crescent. There you go, the in-betweeners. Okay. So this was the slide that I kind of alluded to with synchronous rotation. So I'm back to being the moon. I guess I was supposed to be the moon. And this is the Earth. Okay. The moon spins on its axis the same amount of time it takes to orbit the sun. Kind of from left to right, it took me a while to kind of figure out what your author was doing here. But I'm going to show you the left one first. I'm not going to rotate. Okay, I'm just going to orbit. So I'm the moon, I'm just going to orbit. Okay, that's kind of what she's showing. That's not what the moon does. Okay, the moon rotates and orbits. So here we go. I'm going to complete one orbit. I'm going to complete one orbit exactly the same amount of time. Sorry, one rotation. Same amount of time it takes to complete one orbit. Okay, that actually has the consequence of, as I orbit, I see the same face as always. It's called synchronous rotation. A lot of planets, a lot of moons that orbit planets have synchronous rotation. Same size, always there. So this leads to something, this phenomenon of the far side of the moon. Not the comic strip, but. So the far side is the side that you don't see. Sometimes people call it the dark side. It's not the dark side, really. Okay, because sometimes it's totally lit, sometimes it's totally in the dark. It's just the side that we don't see. There was a, Apollo, it was a sci-fi movie. Oops. Missed my, I'll try to find it here in a minute. But there was a sci-fi movie about the far side of the moon being rock creatures. Like, anyway, it's a terrible movie. I wouldn't recommend it. But the far side of the moon is actually, for instance, something real. When the Apollo missions were orbiting the moon, they would lose communication when they were over there. That when they talk to the UFOs, like the little aliens. Okay. Hopefully after break I'll show you, but the far side of the moon, okay, the side of the moon that we never see actually is really popped, like cratered and everything. And so that's not an accident. Basically, it kind of took the brunt of some of the crap that otherwise would have hit the Earth, kind of after it formed and early on when there was still a bunch of stuff running around our solar system. Okay. Eclipses. We have one coming up we've got it marked on our calendar. I'm going to take a personal day in 2 years from this August. Okay? Eclipses. For whatever reason, I'm sure there's a reason, we definitely can see more lunar eclipses of the moon, than we can solar eclipses. In fact, we have a lunar eclipse coming up. I told you, like September 27th. Yeah, a lunar eclipse, an eclipse of the moon. So for lunar eclipses, basically the moon goes dark. And I'll go ahead and show you how the moon goes dark. I'll go over here. Okay, the moon's going to go dark. Here's the deal. The moon is orbiting the Earth. Okay, and what happens is it goes just right. It basically goes in the Earth's shadow from the sun. Okay, and so it goes from being full, because it's a full moon, because it's over here, to basically being blood red, because basically it's getting very little light from the sun, no light from the sun. It's in the Earth's shadow. Then it comes out, okay, and then you'll see it kind of reappear during the lunar eclipse. The solar eclipse looks like this. So basically, solar eclipses can only happen, remember this is our new moon phase, okay, where my back's lit up, okay, new moon, can't see anything. What happens here is the moon is just right, okay, and it blocks out the light from the sun. The disk of the moon and the disk of the sun are very similar, okay, depending upon kind of the distance between that the moon is from the earth. Okay, so the moon is kind of orbiting the earth and it goes right in front of the sun's disk. Okay, so that's kind of that one. So lunar eclipses can only happen during the full moon phase and solar eclipses during the new moon phase. And I have a slide to kind of show you, I guess it's right here, that the reason we don't have a solar eclipse, okay, and a lunar eclipse, every month has to do with the plane that the moon orbits the earth actually is lying outside of the ecliptic, the plane that the earth is orbiting the sun. So it's inclined about 5 degrees. So that 5 degrees means it's a little kind of a hit and miss as to whether this will line up just right. That's all that means. Okay, so a little bit more about eclipses. So what we have here is a failure to communicate now. What we have here is whether it's an eclipse or not. I think this is kind of cool. The Earth, okay, here's the Earth, casts into outer space kind of a bullseye of shadows. It has an intense part of a shadow called the umbra, and then it has a less intense part of a shadow called a penumbra. Okay, and it's important to kind of understand those two parts of the shadow of Earth to kind of think about what sort of lunar eclipses we can have. So, lunar eclipses. I'll tell you which ones are good. Okay, first off, a total lunar eclipse. See the word total here? Total lunar eclipse. Yes. It's definitely worth getting up at 3 o'clock in the morning for. I've done that before. Dragged my daughter out to the observatory. I got pictures to prove it. Okay, so for a total eclipse, basically the umbral part, the deep part of the Earth's shadow, the moon passes right smack dab through it. And so for this eclipse that's coming up in September, we'll all kind of do a little bit of homework. And NASA is great about putting up information about eclipses. And it will say when and how long it will occur, okay? But the cool part is where it will tell you when is the moon going to go into the umbral part of the Earth's shadow. And that's awesome. But you'll see, when you look on the internet, they'll say, when is the moon going to pass into the penumbral part of the Earth's shadow? And you're like, I can barely even tell anything. Okay? So, total lunar eclipse. Partial lunar eclipse are pretty cool. Okay? Partial lunar eclipse are where you actually would see the moon go into part of the Earth's umbral. Okay? So you'll see a bite taken out of it, but you won't see the whole disk go away. So that one's pretty good. I don't know about 3 o'clock in the morning. Maybe midnight. Okay, maybe. But this other one, I totally would not even do much for it. Basically, the moon is only going to go through the weak part of the Earth's shadow, and you're not going to see much of a change at all. A penumbral lunar eclipse. And if you're like me, you're going to get those terms mixed up. Hopefully not. Penumbral part of the Earth's shadow is the wimpy part. Okay, solar eclipses, we kind of have an assortment. But here you see actually, with the solar eclipse, you have the moon casting a shadow on the Earth. And again, you kind of have that umbral part and the penumbral part. But I don't think the umbral part you see much at all. So the crazy thing about it is, can you see kind of this arrow, the Earth is spinning? So what happens is only during a sweet, tiny moment, a particular segment of Earth's population can see this eclipse happening. Okay, so that's a total solar eclipse, and I have a picture coming up. Okay, an annular solar eclipse is when the moon, and you probably can't tell it from here, but the moon is just a little bit farther from the Earth. So when it casts its shadow, okay, the sweet part is just a little bit short of the Earth's surface. So here we go. That is a total solar eclipse. Taken with, looks like, and we'll talk more about this later, but it looks like it was taken with film specific for catching the chromosphere of the sun. If you were looking through a telescope safely to watch a total solar eclipse, you would not see that. That's my point. A partial solar eclipse, when a bite is taken out of it. Honestly, a partial solar eclipse are cool, but you're not going to notice it unless you have a telescope or welder's glasses. That's something safely to protect your eyes. And then here's what an annular solar eclipse would look like, where it kind of looks like a ring. Okay, this is where the moon is just a little bit farther. You know, we talked about apogee being when the moon is farthest from the Earth, okay, to make that shadow hit the Earth. All right, so eclipses. This is a solar eclipse. Very cool. Okay, this actually is showing you solar eclipses, the paths they'll take through the year 2038. Where are you going to be in 2038? Okay, and this actually is listed on here. Will be, is that right? Wait. August, that's not right. Oh, those are lunar eclipses, sorry. Yeah, no, the solar eclipse that I want to catch, there it is, right there. Because that one's lunar eclipses. Right here. School will have started, we've looked ahead. My husband and I are just going to make sure we catch it. So we're thinking St. Louis, and the latest is that I'm going to try to see if there is an astronomy club there that we can come crash on. Okay, so I think it's like a Monday or something. So mark your calendars, okay, for this one, not the partial lunar eclipse. Okay, so to kind of finish up with a topic that actually is going to come up again in the next chapter when we talk about kind of how over time we came to understand what we know about our neck of the woods. Okay, so constellations are constellations, right? Constellations make out pictures, and those pictures are always the same. The Big Dipper is always the same. The Little Dipper is always the same. You know, Orion's wonderfully the same. But the deal is those pesky planets. Okay, remember, planets will shine as the sun hits them, and that light is reflected back to us. I think that is so cool too. Okay, so that's why we see planets in the sky. But the planets, you figure, let's go back to the sun. I'm changing gears. This is not the Earth now. This is the sun, and I am the Earth. And I've already kind of told you that the other planets also orbit, you guys know the other planets orbit the sun too, on this ecliptic. Okay, so as they change in their position, we are actually going to see them, because they're pretty close, planets are pretty close compared to the stars. We are actually going to see the planets move against the background stars. The word planet means wanderer. But they're not, I was thinking the other day, this word wanderer almost implies like they just, I don't know where they'll be here, and then a planet will be over here. But they're very orderly. They are on what we call the ecliptic. That Stellarium software I showed you, the Stellarium software actually will draw you a line, the ecliptic. And that is where you find your planets. Okay? So they're not really wandering. Now they will, because they're orbiting the sun in the same direction, they will have what we call direct motion, okay, which means that they move eastward against the background stars. This is not in the same night. This is like night after night after night. That is what we call direct motion. Sun moves against the background stars. That's why we have the constellation zodiacs. Okay. Sun also moves eastward. Okay. So this kind of eastward motion of the sun against the background stars and eastward motion of those wandering pesky planets, actually, we could still have that if the planets orbit the Earth. I know it's weird. I know it's weird. And if the sun orbit the Earth. Because honestly, up to Galileo, 1600s, that's what they thought. Well, not all of them, but the prevailing thought. But what happens is the planets tend to go what we call retrograde. I'm sure that's an astrology thing too, but it's a scientific thing. The planets tend to go westward for some time, okay, for a short period of time, and then continue eastward. Eastward, 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 eastward. Oops, I'm going straight. Eastward, okay. So this actually is Mars. These are showing Mars against the background stars. And no, Mars is not going to be as big as the moon in August. That comes around every August. Like, no. So here we have direct motion. Okay. June. Okay, here about July, it goes retrograde. Switch my colors. Retro, 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 retro. And then it goes back to direct motion in September. Okay? So it goes backwards. And you're like, oh, that backward motion can't be explained if the planets are orbiting the Earth. Okay? So they need to explain that. And actually, we're going to come up with, it's weird, but a guy named Ptolemy in chapter 3, we're going to see the Ptolemy actually came up with an explanation for that. But I'm going to go ahead and kind of let the cat out of the bag. We can explain this backward motion, this retrograde motion of planets, if we go ahead and assume correctly that all the planets, the Earth and the other planets, orbit the Sun. So here is your look at how does putting the Sun in the center of the planet's motion, how does that explain the backward motion? Okay. Before I kind of talk you through it, see if this works for you. So you're driving down the road. Okay. You are in the fast lane, right? I don't know if you should be or not, but you are in the left lane. Okay. Slower traffic is over here in the right lane. So let's just say that right here is my slow-moving vehicle. Okay, and I'm approaching them. Okay. As I approach them, they appear to be going this way against the background. Okay. They're going this way against the background. Okay. When I get up next to them, they tend to kind of look like they're going this way with the background, the other direction. And then after I pass them, then of course they look like they're going the direction they were with the background. I know haven't you ever felt that sensation as you pass somebody and kind of looking over? Well, next time try to, so you kind of, they look like we look normal, and then they look weird, and then they look normal again. It's a strange sensation. But that actually kind of overcoming sort of deal is why planets appear to go retrograde. Almost sounds like those go rebel, right? Planets appear to go backward against the background stars. So the example we have up here now, okay, the blue is us. That is the Earth. The red track is Mars. One of the things that Kepler, we're going to talk about this in chapter 3, found is that the farther out the planet is, not only does it have a bigger orbit, but it just moves slower. So the Earth actually overtakes Mars in its orbit. Well, that means that Venus actually overtakes us, which is true. Okay, so the closer you are to the Sun, the faster you're going to go in your orbit. So this actually then is these first positions, this position 1, position 2, and position 3, 1, 2, and 3, they are all normal. They're normal direct motion. Okay? We are kind of catching up to Mars. They're about 3, 4, and 5-ish. 3, 4, and 5-ish. Okay, we are overtaking Mars. And Mars appears to go opposite direction. Once we get securely past Mars, then it goes direct motion again. Okay, so that is actually, and I don't know. It's something you need to maybe mull over in your mind, but it's true, okay? So the point is if putting the sun in the center of a planet's motion explains retrograde motion, then why not go with it? Well, there's one other thing I need to, before we have a break here, okay? There's parallax. And like I said, if you went to it, and this will be another good little exercise after you find the word you need to fill in. So look at something kind of in the front of the room and hold your finger to your nose and close your eyes, one at a time. Does it look like your finger is in a different position against that thing over there? Okay. That's called parallax. Okay. Now do this with your finger kind of at a similar location. Put your finger out farther. And go ahead and wink back and forth again. Or cover your eye, okay? Wink back and forth again. Do you see that it relocates, but it's not as far?
It doesn't move as much.
It doesn't move as much. Exactly. And here's the deal. If I were to go ahead and take something like this and move it, let's see, I'll do it for you guys. So I'm gonna move this up here, okay? So go ahead and try to wink back and forth and see if don't move your finger this time, just see if that black podium looks like it moves in a different location.
Mine does because I have contact and it looks like it goes further away, closer.
Now let me move this closer, and it's not your finger, but I'm going to move it closer. And let's see if, and it won't work for you, Susan. But maybe you can work it over there. So look at the podium and wink back and forth, see if it moves.
Closer.
Not much, does it?
Oh, mine moves a lot.
Does it? Oh, you don't count. And this is, the closer an object is to you, the more you're going to see parallax against the distance. We did that good, okay? Less, okay? So here's the deal. Actually, back in Galileo's time, the people were kind of contemplating these things. I'm like, dude, you really think that you think the Earth goes around the sun? Well, look at this. If we went around the sun, just like this figure, you see this figure seeing? If we went around the sun, as we look up at those stars, we're going to kind of see them. It's kind of like closing your eyes. Here is one way. 6 months later is another way. We should kind of see those stars move against the background. They should scramble. And later on, part of what Galileo said is, you know why we don't see parallax? It's because they're so damn far away. They're so dang far away. Okay, it's kind of like the podium being up here. Okay. But actually, like this slide says, we can use I don't know, Hubble Space Telescope images or some fancy telescope, and we do see some wiggle in stars. We do see a certain amount. Okay, we do see stars move a little bit, some stars. The closer stars, we see parallax. So parallax seen with stars look like this. So over here in January, okay, here we are in January, we look up at this star, and we see it kind of hanging over here. 6 months later, okay, we're in July, okay, we're looking up at the star, and we're going to see it hanging over there. Okay, it's kind of like, if it's a nearby star, it will move against the background stars, and actually we can use that to get to distance of stars, some parallax. But in general, my point is they did not see parallax. So the Earth cannot be moving. All right, so let's take a break and come back and knock out chapter 3 after break. Woohoo!